To interpret text as a programming language, you first need to parse that text into some structure that makes it easy to perform interpretation. We've seen that scheme code is fundamentally tree structured. It has expressions within expressions within expressions. But the way it's typed out is with a lot of parentheses in a row. It's just text. And parsing is the process of converting that text into an expression tree so that the code can be evaluated according to the rules of the language. Since a scheme program just looks like a scheme list with parentheses and symbols and numbers and such, we're going to write a program that reads scheme lists and converts them into a representation of those lists that has the right structure, the first element and the rest of the list. But we're going to do this in Python. A scheme list is written as elements in parentheses, but the internal structure of this is that there's some first element and the rest of the list. Each element can be a combination or a primitive, and so I could have a scheme list that looks like this. The symbol plus, another list with the symbol times, with the number 3, with another list, etc., etc. The task of parsing a language involves coursing this string representation, which is just full of spaces and stars and pluses and numerals, into an expression. And in scheme, an expression is just a scheme list. So there's a Python program called Scheme Reader, which you'll have a chance to implement part of. But let's talk about what it does. It takes in text, like 1, 2, 3, and gives you back an expression. Now that expression can be made out of just numbers, or it can be made out of pairs. A pair is what you get when you combine the first and the rest of a list. So the pair class is really simple, just has a first and rest attribute. But what's interesting about the pair class is that when you create a nested pair, pair 1, pair 2, nil, like a linked list, and you print it out, you see how Scheme would write it. So if I write 1, 2, 3, I get an object, which is a pair. Its stir string is the scheme representation of this list, 1, 2, 3. But its repr is how we're going to represent it in Python, as a pair with 1, followed by a pair with 2, followed by a pair with 3, and nil. And what is nil? Well, actually, there's a nil object, which is just an instance of the nil class, which has a repr string nil, and a few methods defined on it, which you can learn about when you work on your project. Scheme Reader is a program that takes parentheses and numbers and gives you some nested pairs. But it does it in a very flexible way. So if I want to put 1 in, then 2 and 3 into a structure, then it knows that this is a list within a list, which represented using linked lists, which are pairs, means that you have an element 1 and an element which itself is a list. And therefore, we can represent scheme code. Now, you might think the stir is always the same as whatever you type in at read, but that's actually not true either. What's happening is that it's going through what might span multiple lines, might have all kinds of crazy spaces in it, and might even have numbers that are multiple characters long, like 4.5, and maybe there's 6, 7, 8. And if I close the parentheses correctly, like that, it's going to put it all together into one nested pair, and then this stir string is just what you get when you print out this nested pair structure. So scheme read has to know that when you have 4.5, that's really all one number, not two different things. But when you have two parentheses in a row, those really are making two different pairs. And that process of going from this text to this structure is called parsing. So this thing is a scheme list with the first and a rest, and that's exactly the structure we're building. Parsing actually has two parts. It takes text, it returns expressions, but it does so by first performing lexical analysis in order to get a sequence of tokens, and then syntactic analysis in order to get an expression. The original text, for example, can be 3 different strings on 3 different lines. But the job of lexical analysis is to convert each line into what are called tokens, which are individual strings and numbers representing atomic units within the programming language. The interesting one here is that 2 and 3 are combined together into the number 23, even though there's no space here, the closed parenthesis is part of a separate token. And that's just a fact about scheme and how it works. Also, the extra white space is discarded in the token representation because it doesn't matter. 5.6, the lexical analysis knows, is another way of writing down a number, and so it becomes its own token. This is an iterative process that checks for malformed tokens, determines types of tokens, and processes one line at a time. This is not something you'll ever have to write. Instead, we've written it for you. And if you ever want to try out the tokenizer, you can type in some string, 1, 2, 3, 4, and it will tell you that those are 2 different tokens. Or if you have parentheses within parentheses, then it will tell you that each parenthesis is a separate token, but these 1.2 all goes together as part of one number. Then syntactic analysis puts this into a tree. That's what we just saw. Some pair that has pairs within it that represents the entire scheme list that is this block of scheme code. This is a tree recursive process that tries to balance the parentheses and returns a tree structure. Instead of representing it as a Python tree class, we'll represent it as a pair class. But since pairs represent lists that contain other lists, you can think of it as a kind of tree. And it does process multiple lines by combining things together until it finds a closing parenthesis that matches the opening parenthesis. Syntactic analysis, which is an interesting problem to try to implement, identifies the hierarchical structure of an expression, which may be nested. It does so by calling a function schemeRead that consumes input tokens for exactly one expression. It has a base case, which is symbols and numbers, and it has a recursive call, which is that whenever there's a sub-expression, it calls schemeRead on it to combine it into an expression, which then can be placed into a larger expression. So calling schemeRead on this sequence of tokens starts at the beginning and isn't going to return until it finds the parenthesis that matches that one. So it recursively calls schemeRead to figure out that that's a simple base case of plus, that's a simple base case of 1, but the next call to schemeRead is actually going to read a whole sub-expression. The next call to schemeRead is going to read a whole sub-expression, and the original call to schemeRead is done when it finds that the next thing is a closing parenthesis, which matches the opening one at the start. This is something that you'll have to work out how to write, but there's a long description in the textbook about how to go about it, and I'd encourage you to spend some time learning how to write syntactic analysis for a parser.